In the third and final part of these videos, I'm going to look at the energy stored in a capacitor. And we need to remind ourselves of the graph of voltage against charge. It's a straight line through the origin. Now, you will already remember the formula that goes E equals QV. So you'd think, well, that's easy. The energy supplied is QV. Well, this is equal to the energy supplied by the cell. And we might refer to V as V naught. Because when we charge up our capacitor, it will go up to V naught, the voltage of the cell. And this formula is, you can look at it two ways, really. First of all, we can say, well, volts is joules per coulomb. So if we've got a 12-volt battery, that means it gives 12 joules to each coulomb. And so if we want to know how much energy is delivered, we just multiply by the number of coulombs. But the important thing here is that every charge gets the full 12 joules. But we can see from our graph that when we discharge the capacitor, then initially the charge will have 12 joules of energy, but as time goes by, that voltage will come down. Now, earlier I showed you a sort of analogy of water falling down in a column, from a height. And we can say, well, okay, we started off at height h. So you might say, well, okay, the height fallen is h, therefore the potential energy is mgh. But that would assume that all the water was at the height h. And some of the water wouldn't be falling the full height h, it would only be falling much less than that. So in the same way, what we've got to do here is we've got to say our discharge, the energy delivered, is going to be the area under the graph here. So the energy supplied by the cell is quite simple, but at discharge, the energy released by the capacitor it's going to be the integral of V dq. So that's the area that I've shaded, and so we can see straight away that it's just going to be a half because it's a straight line graph. And then we can say, but Q equals CV, and therefore if we substitute in there, we get a half CV squared, and whether you put the naught in or not doesn't really matter. B is the voltage of the battery, and as time goes by, the voltage will reduce, and as a result, instead of the energy given back from the discharge being QV, it's only a half QV. Now, the other analogy for this is the Hookean spring. So I'll just draw another little graph over here. So you may remember with the Hookean spring, we're doing work done equals force times distance. But unfortunately with the Hookean spring, when it does work, it only starts off at the maximum force. And the force goes down as the distance is covered. So again, the work done, which is equal to the energy stored, the elastic strain energy stored, is going to be the integral of f dx, and that will be a half fx, which equals a half kx squared. So if this is analogous to the idea of the capacitor, and so we find that actually, although the battery has provided QV, we only get a half QV back again. So this asks the question, what happens to the other half QV? So I'm going to finish this video series by looking at what happens to the other half QV and showing that whatever the value of R, the other half QV is dissipated as heat in the resistor R. So if you remember, let's go back to, we've got our capacitor here, and we've got our resistor, and we've got our switch, which we're about to close, and we've got capacitance C, resistance R, and we start off at V0, time t equals 0, and then we close the switch. And then we get the exponential curve for voltage against time, starting at V0 and going like this. As the voltage goes down, the current goes down similarly. And to calculate the total energy dissipated, the energy dissipated in the resistor, well, we know that P equals IV. Oh, but the current's changing and the voltage is changing, so power is a function of time. So if we're going to calculate the energy dissipated, we're going to have to integrate the power with respect to time from time t equals 0 right through to time t equals infinity. Well, you can't integrate P power with respect to time unless you can express P power in terms of time. So let's see, but P equals IV, that's the dog, and we've got an equation for I, and we've got an equation for V. We got those higher up here, I think they were in blue. There's the one for I equals I0 e to the minus t over CR, and there's the one for V equals V0 e to the minus t over CR. So they both have e to the minus t over CR, and we can put them in here. Okay, well, I can feel an integral coming on. It's the integral between 0 and infinity. The current is I0 e to the minus t over CR, and the voltage is V0 e to the minus t over CR. So if we multiply e to the minus t over CR by e to the minus t over CR, we get e to the minus 2t over CR. And now we can integrate that with respect to time. The I0 is a constant. It's the current at time t equals 0. V0 is also a constant. It's the voltage at time t equals 0. So I can leave those two out of the brackets, and then I've got to integrate this fella between 0 and infinity. Here we go. Well, e to the minus 2t over CR, when we integrate it, we get something that looks pretty similar, e to the minus 2t over CR. But if we differentiated that, we'd get minus 2, so we need minus a half. And we'd get divided by CR, so we need to multiply by CR. Okay, then we're going to put the limits in. When t is 0, e to the 0 is 1, and when t is infinity, e to the minus infinity is 0. So we just get the minus sign disappears, and we're going to get half I0 V0 CR. Have I got that right? You might like to stop the video and just check that I have indeed got that correct. I'm pretty sure about the half, but what about the I0, V0, and CR? So what are we going to do next? I should think I can feel a but coming on. But V0, oh yeah, V0 equals I0 R. So we get a half I0 squared. Is that the way I want to go? V0 squared C. Oh, I think what I'll do is I'll say I0 equals V0 over R. Oh yeah, so here we're going to get a half. Oh, I0, hang on, I0 R equals V0. Oh, half C V0 squared. Gotcha. Because V equals I0 R. So I0 times R equals V. Absolutely. Let's eliminate the I naught and the R. So we get a half, and there's the C, and we get V naught times V naught is V naught squared. And that is equal to a half Q naught V naught. Hang on a minute. We were trying to see where the other half went. From up here, we could say, okay, the energy stored in the capacitor, instead of being a whole QV, it's just a half QV. We've had little noughts in here if we want to indicate the time t equals naught. You have another little naught in there if you like. So Q naught and V naught are the maximum values of Q and V at time t equals naught. What we found down here is that the other half, Q naught, V naught, is dissipated as heat in the resistor. Well, that's just as well. I would say, phew. What we proved is that regardless of the value of R, exactly half the energy will be wasted, dissipated as heat in the resistor, regardless of what the value of the resistor is. You might say, well, a lot of the time the value of the resistor is zero. Well, it's never quite equal to zero. Even wires have a certain amount of resistance. So the phew is that energy is reserved. Not reserved, conserved. So if you found that proof a little bit tricky, take time out to go and have a cup of coffee and come back and visit it again. Okay, so that's all we've got time for, and I'm signing off now. So the next job is to try some examples.